Okay, let's pick it up. I don't know what happened. I hit something. My palm hit something on this iPad, but let's do a brief recall here. So if we were to look at the current as a function of voltage, and I then is equal to 1 over R times V, we get a straight line, and the slope then is going to be equal to 1 over R. 1 over R is the slope. We defined that to be G, the conductance. And I think we were looking at the units on the conductance. And so the units then are going to be 1 over R, which then has units of reciprocal ohms. As I said before I lost you, that the unit can also be written as the mho, and which I thought was pretty clever, since mho is ohm spelled backwards. And I think, as I said, hopefully it's in the last video. Physicists actually have a sense of humor. The SI unit, however, is called the Siemens, and that's given a capital S. So you'll see all three of these, again, depending on the context. The conductance is actually used quite often in biological areas. One can talk about the conductance of an ion pump in the membrane. It's typical to talk about conductances rather than resistances in that context. And so some of you might encounter that. You won't find a discussion of the conductance in the textbook, so just wanted to bring that out. So what I want to do now is do a couple of Gedanken experiments, right? A couple of thought experiments. And so imagine that I have a chunk of conducting material, and this is then length L, and I have another chunk of conducting material, and it has length 2L. Same cross-sectional area, A, and they're both hooked up to the same battery voltage, V. So everything's the same in this scenario, other than the length of the conductor. And so we now want to look at the relationship between the resistance and number of collisions that a mobile charge carrier will have. And so I hope it's clear to you that as a mobile charge carrier moves through this chunk of conductor under this voltage, that the number of collisions in a conductor of length 2L is going to be twice the number of collisions that a mobile charge carrier will suffer in a conductor of length L. And so then the current is then going to be related to related to the inverse of the resistance then, number of collisions, right? Because R is related to the number of collisions. Which means that the resistance then is inversely proportional to the current, and that the resistance is then going to be proportional to the length, okay? So here's the important part here, right? So since the resistance is related to the number of collisions, that, and again in a linear fashion, right? Clearly, if this conductor has a bazillion collisions for a mobile charge carrier and going this length, it's going to have 2 bazillion collisions in going through a conductor of length 2L. And so the resistance then is going to be proportional to the length. And again, we really don't even need this relationship in this analysis. So we could just get rid of that. All right. So looking at the next experiment, say now that we have two cylindrical samples of a conductor, and this one has cross-sectional area A, length L, and I connect it to a battery of voltage V. And then what I do is I have a chunk of conductor here of the same length, but now the area is 2A, and I connect it to the same battery voltage V. And I now look at the number of charges that move past me per unit time. And I hope it's clear to you that if I were to have a bazillion charges move past me per unit time in this conductor, then I would have 2 bazillion charges move past me in this conductor in the same amount of time. So then the current is going to be directly proportional to the area. The larger the area, the larger the current, okay? Because remember that current is amount of charge per unit time, right? This is constant, and so the amount of charge moving past me is going to change. And so now by Ohm's law, right, current is going to be equal to voltage divided by the resistance. So then 1 over the resistance is going to be proportional to the area. Okay. Let's see here. And so the resistance then is going to be proportional to 1 over the area. Okay? And so that's worth a box. So what we have here now is that the resistance is going to be proportional to the length and inversely proportional to the area. Now to make this an equality, I need a multiplicative constant. So again, we assumed in both of these thought experiments that the material was the same. So if we used cylindrical samples of copper, then both of these would be copper. And in the bottom experiment, both of these would be copper as well, okay? So the material would be the same in both thought experiments. So we need a material-specific factor in here. And so we can convert this to an equality with a factor now, which is called the resistivity, right? So we got to be careful here, right? So this is the resistivity, all right? This is the resistance. This is the resistance. Rho is the resistivity, right? Not to be confused, with the density, okay? Only so many letters to go around, both in Greek letters and in I guess they're Aramaic letters, but someone can correct me on that. So, so the resistance then is equal to the resistivity times the length divided by the area, okay? So let's look at the units on this. So the units on the resistance are ohms. The units on length are meters. The units on area are meters squared, which means that the units on the resistivity must be ohm meters, not ohms per meter, but ohm meter, okay? And so the larger the resistivity, the larger the resistance of a material, okay? So again, you could look up a table in your textbook of resistivities and get a sense of their scale. Now recall, and again this is not in the textbook, that the conductance was equal to 1 over the resistivity. And so then the conductance is going to be 1 over rho times the length divided by the area, which is going to be 1 over the resistivity times the area over the length. So let's see how this works, right? So we have resistance. We have resistance R, conductance G. We have resistivity rho. What do you think we're going to call this? This is going to be the conductivity, and that's going to be called sigma, all right? So we have resistance, conductance, and resistivity and conductivity. So the conductance then is going to be equal to the conductivity times the area times the length of a material, okay, and that's worth a box, all right? And again, this discussion is not necessarily in the textbook, and so again, I bring it out only because in biological and chemical areas, the conductance and the conductivity actually play a bigger role than the resistance and the resistivity. Okay, so again, I just want you to be familiar with the interrelationship between those. Okay, so I think I'll end that here, and then we'll pick up on part 4, and then I think that will come close to ending this chapter. Very good, folks. So by later today or Sunday, I will conclude chapter 26, and then we'll move into some basic circuit stuff in chapter 27. And again, we'll move through that rather quickly. Alrighty, take care. Have a good weekend.